All right, so let's go ahead and get started. So today is going to be the first day that we're going to be using learning catalytics. It's not going to be for a grade today, but I would like to start using it so that we're getting in the habit. And if you haven't used it before, this will help you get acclimated to it. Yeah?
Just to be honest, I think like half the class doesn't know how to get their learning catalytics.
Okay.
How to use it.
Okay, sure. Let's go through that pretty quickly then. So, yeah. So you can find learning catalytics directly from the Blackboard page. So what you want to do is, if this is, so we want to find the meta course, and I teach several classes, so it's always hard for me to find what I'm looking for. So this is the right one. Okay, so this is the main Blackboard page. Has everybody been able to find this so far so they can look at the syllabus? Yeah, I apologize for it taking us a while to get everything up there. We were having, it's technically difficult to get all of the sections together, and we have somebody that works with us from Blackboard that does that for us, and it's the beginning of the semester, so they were bombarded with a lot of different problems. But now we have our meta course set up here. So this is where you're going to be able to find all of the homework assignments. It's also where you can find the syllabus. So if you haven't looked at this already, you can find the syllabus right here. Like I said last time, the syllabus is more or less the same as it was last semester with some new information. I'm not going to spend too much time going over this, but it's there for you to look at. So to get to learning catalytics, it's actually pretty similar to the way that you're going to find where the homework is. So you go to Mastering Physics, and then Welcome to Mastering Physics. Load, and then go to Learning Catalytics here on the right. Now this is something that you have to pay for in kind of the same regard as the clickers. So you have to have a membership for that. But once you get that membership set up, you can log in here. Has anybody? Yeah.
I actually was on the phone with these people earlier today, and they said that
I refer to them the same way. These people. Okay. Yeah.
It's not set up so any of us can see it.
Oh, okay. Well, I guess we still have some work to do on the technical side. So for the time being, this is where you're going to have to go to look these things up. We're not going to actually use it in class today then if nobody can access it, and I'll try to figure that out for Tuesday, hopefully, and if not Tuesday, then for Thursday. Okay, so don't worry about this right now, but just be aware that that's going to be the way that we're going to do the in-class assignments. And if you happen to be sitting next to somebody that was in my section or Dr. Souza's section, can those people raise their hands so we know who those people are? If you sit near one of these people, they've used this before, and if you have questions about how to access it or to set it up, they can answer them probably a little bit better than I can, because I don't look at it from the student side, I look at it from the instructor side. Okay, so with that out of the way, let's go ahead and actually get started. So to begin with, I have what is no longer a learning catalytics question, just to get us to warm up and remember some of the things that we talked about last class. So if you bring a positively charged rod close to a small piece of material, in one case the material is made out of metal, in the other case it's some insulating material, what's going to be the force that each material feels towards the object that you're bringing towards it? Go ahead and talk to each other and figure this out. Okay, so let's go ahead and talk about this one. Anybody care to offer their answer? Yeah.
I picked B because insulators distribute the charge over the entire body, and then metals, the electrons can flow freely, so they can distribute to be attracted.
Right, so half of that's right. Okay, but you're on the right track, and you have some good intuition about the two. So we know that the metal allows the electrons to move around, right? So if I bring something that is negative near a metal, we remember that we have some atoms in here, and if this is a metal, what's going to happen to all these electrons when I bring this negative here? They're just going to move all the way over here, as far away as they can, right? It's going to move all the way over here. So that's what's going to happen with the metal. So when it polarizes itself like this, then clearly this is going to be attracted because you have more positive on this side and negative on this side, and it's closer here. So the positive and the negatives attract. Now, what's going to happen with the insulator? So you are correct that the insulator is neutral, and that these electrons are not allowed to move away from their associated atoms. Do we remember from last class what happened here? Yeah.
The electrons don't necessarily move, but the atom just reorients itself.
Right. So the electrons, they're locked into their atoms. They're not allowed to move all the way over here. But what they will do is they'll move as far away from the charge as they can, the negative charge that we have over here. And so again, this polarizes it so that the left side is positive for every atom. The left is positive and the right is going to be negative. Now, something that I noticed in watching the videos back last time, a lot of people said that the reason why these are attracted is because something is negative and then something's neutral, and so there's a difference in charge here, so it's attracted because this has some charge and this doesn't have charge. That's not quite true, because it's not attracted because it's negative and less negative. It's attracted because of this process that the atoms in the material undergo. So they'll orient themselves in a different setup if it's a insulator, or they'll completely move to the other side if it's a conductor. Okay. Any questions about this one? It's a good start. Okay. So now let's move to the next one. I've already lost my slide changer. Okay. So something that we're pretty familiar with, we live in the 21st century and everybody orders everything off of Amazon, right? So you get boxes full of packing peanuts, and you'll notice that when you have a box full of packing peanuts and then you have something that's cellophane wrapped in there, what's going to happen? They'll stick, right? So we want to understand why they stick. Does anybody want to offer a reason why they'll stick? Yeah. Friction's part of it, right? So friction is going to move charges around. It's going to take charges off, and so you end up having a net positive charge on one and net negative charge on the other one, right? So these rub against each other with friction, and then you end up removing some of the negative charge from the packing peanuts, let's say, and that leaves the cellophane wrap with a net negative charge. And because you remove those electrons from the packing peanuts, they're left with a net positive charge. Good. So the next thing that we'd like to talk about is to kind of go back to something we talked about last time when it comes to insulators and conductors. So go ahead and talk to each other about this one. What happens if I deposit a charge on an insulator versus if I deposit a charge on a conductor? Okay, so what do we think is going to happen here, guys? I have a metal and I deposit some electrons on it. What are going to happen to those electrons? How about somebody in the back? Do not point at people with a laser pointer. How about people in the back? What do you guys think? I got a metal and then I put some negative charge on it. What's going to happen with those negative charges? Yeah.
I believe they're going to spread out.
They're going to spread out. Why?
Because they're going to start distributing themselves around with the other.
This is true. Yeah. There's a real why here that I'm trying to get to. Anybody know why they're going to spread out? Yeah.
Because when they transfer the charges, the charges can move around. So you put negatives into neutral metal. The positives will move away from negative charge, and you spread them out all over the metal versus insulator where they're locked in, they can't move anymore.
That's partially true, right? So if I have some material, it's going to have some positive and negative charges in here already, right? And the negative charges certainly don't like the positive charges that are here. But what we can imagine is because these are already in pairs, that the things that are happening with the atoms in here actually aren't important to what's going to happen to these negative charges. right? So we can actually kind of imagine that they're not here at all. And so really what we're doing is I'm just throwing a bunch of negative charges on here. And at the instant I throw them on here, they're like this, right? And we say that they're going to spread out. And not only are they going to spread out, they're going to spread out evenly, right? So when they spread out evenly, they're going to look like this in the end. And the question that I'm still looking for the answer to is, why is it they're spread out evenly? Yeah.
Because they repel each other?
Exactly. Because these are negative charges, and negative charges don't like each other, they're going to spread out as far as possible from their adjacent negative charges as they can. Okay. So what's going to happen if I, instead of putting this on a metal, I put it on an insulator? What's going to happen then? Any guesses? So what was the primary quality of a metal? Why do we care about metals? What's allowed to happen in metals?
The electrons are allowed to move.
Electrons are allowed to move. So if in a metal electrons are allowed to move and in insulator electrons are not allowed to move, what do we think is going to happen when I put these on here if it's an insulator? Somebody said something over. What's that?
It's going to be spread throughout the material.
It's not quite going to be spread throughout the material. So that's true. Yeah. So if I stick a bunch of negative charges on here at some time, like initial time t is equal to 0, these charges that I stick on here, they're stuck. They can't go anywhere. They're not allowed to flow because it's not a metal. And what will happen though is this is going to polarize this, so that if I had all of these pairs of positrons and electrons here that are randomly oriented, these are going to reorient themselves again, so all of the negative charges are still attached to their atom or to their nucleus, but they're going to be as far away as possible. Okay. So you guys see the difference here? When I put the electrons on a metal, they spread out as much as they can, because you're allowed to do that in metals. And in insulators, you can't. Did you have a question? You tricked me. You guys want to trick me? Put your hand on top of your head. I think you have a question. Okay. Any questions about this? Okay. So the next thing we're going to do is continuing with some of the things that we talked about last time. This one's just really quick because I actually have a demo that I want to do with it. When we had our electroscope last time, and we brought this negatively charged bar close to the top of the electroscope, what happened? Take like a minute or two to remind yourselves what happened. Okay, so what did we say? We actually did this exact question last time, right? What happened here? Legs moved apart. Why did the legs move apart?
Because all the electrons are left on the bottom, and then they're going to repel each other.
Right. Metals electrons are allowed to flow, right? So the electrons that are in this bar are going to force the electrons that are in the metal to move as far away as possible. And when they do that, they're going to be equally spread between these two legs. And because then this has a net negative charge, these are going to repel each other. Okay. So now we're going to do the same thing with this demo that I have here. So the arrangement's a little bit different, but the concept is really still the same. So I want you guys to predict. I'm going to charge this, I guess this is an acrylic bar, by rubbing it, and then I'm going to bring it close to this, this electroscope that I have right here. So I want you to predict what's going to happen. All right, so let's do the experiment. What do we think is going to happen to this piece right here? It's allowed to move around. It's going to turn. Is it going to stay? Is it going to get more stuck to here, or are there going to be 40 years of darkness, earthquakes, and volcanoes? Well, hopefully not D, right? Okay, well, let's see what happens. So I'm going to charge this. I'm going to bring it close. And, well, I'll tell you that the answer is not nothing. So when nothing happens, that means I either didn't get enough charge here, or I should use a different rod. Okay, I can hear that one. There we go. Okay. So this works exactly the same way that the last one did, right? The electrons in this are going to repel the electrons in the electroscope, and it's going to cause it to move away. Now, the next question that I have for you is, if now I ground this, so I touch this while this is close to it, what's going to happen? Is it going to repel it more? Is it going to return to where it is? Is it going to stay exactly where it was? Or are the dead going to rise from the grave? So let's see what's actually going to happen here. What did you guys think? Nothing? Is it going to return to where it was originally? Is the bar going to be even more repelled? B? Why? You guys should know I always ask why, right?
You're giving the electrons another path.
Right. So I'm allowing the electrons to leave. They always want to be as far away from this rod as they can, right? And when I ground this, I'm allowing them to leave. And so what that does is it makes it so that these won't repel each other anymore. Okay, so let's see this. So atmospheric conditions and so on. This is actually very weather dependent. Somebody was asking about K. Was it somebody in this class in Coulomb's law K? The reason why this isn't working is because of K, actually. Because K changes with humidity. Try it one more time. I think the other two demos will work better. Okay, so this one's not going to cooperate with this, but like I said, you don't believe me. Okay, well,
Wasn't it one of the videos that was?
it was one of the videos. So this goes directly back to something that we did last class with a video, and I'll try to get this next week as well, so I can shun the non-believers. Is that Charlie the Unicorn? Yeah, okay. So then the next thing that I'd want to ask, if this was cooperative, is once I move the rod away, what's going to happen after I've grounded it? It's going to repel, right? Because that's left with a net positive charge afterwards. So this is what's called charging by induction, because what I'm doing here is I'm forcing the electrons to go somewhere else, and then I ground it, and then remove my hand, and that's left with a net positive charge because the electrons wanted to leave. Okay. All right, so now we get to the next one. So this is what's called a Van de Graaff generator. Does anybody know offhand how this works? It's actually in the diagram here. I don't even. Right. Oh, actually, I didn't. Let me go back to this joke at the bottom here, just so you guys don't think I'm crazy. This is a quote from Ghostbusters. So, 40 years of darkness, earthquakes and volcanoes, dead rising from the grave, human sacrifice, cats and dogs living together, mass hysteria. Okay. Okay. So to get back to the actual physics, so what a Van de Graaff generator does is it has this belt, which works much in the same way that this does, right? So what I was doing when I was rubbing this was I was removing electrons or putting electrons onto this. This is going to do the same thing, right? So this belt, there's a brush at the bottom and a brush on the inside of here, and as this moves around, it's going to be removing electrons from this brush, and it's going to be depositing them on here. So that allows us to get a large positive or a large negative charge on this. Okay. Let me see, where's my slide changer? Okay, so remind myself what I was going to do with this. Okay, so I'd like you to make a prediction. If I put these pie plates on here, what do we think is going to happen? Okay, so what do you guys think is going to happen? Any guesses? So let's remind ourselves what's happening here. I'm making this electrically negative. These are what? Insulators or conductors? Conductors. What's going to happen with the conductor? The electrons are going to move as far away as they can, right? Does that include moving into these? Yeah. And so when it does move into these, then these are all negatively charged, right? So if these are negatively charged, how are they going to act towards each other? They're going to repel each other. All right, let's see what happens. Let's get out of the way so it doesn't hit me. Now we have the same demo that I'm not going to do because it makes a mess, but this is with packing peanuts. Did you guys really want to see this? Yeah. Okay. Well, we have graduate students, so I'll make them pick it up. Okay. Ooh, just charge myself. Okay. All right. More. I'm only going to pick these up once. Okay. So this is to ground this, right? So I need to remove the charge from this because if I just remove the charge with my hand, I electrocute myself, right? Okay. I'll leave this for now and then pick it up later. So I have another apparatus here that works in a very similar way to the Van de Graaff generator. What it does is it has brushes and it's going to separate charge. Now what's special about this one is this has two capacitors on this. We haven't talked about capacitors, we will later in the semester. Does anybody know offhand what capacitors do? Yeah.
They store the charge.
Right. Capacitors store charge. Okay. So let's see what happens when I crank this up, remembering the capacitors store charge.
Oh my God.
And this, again, because of K, might not work as well as we'd like. Okay. Now, if it wasn't so humid in here, this would I could build up even more charge and I could make a larger arc here. Let me see if I can get it going for a while and then get a bigger one. Nah, it's going to be uncooperative today. Okay. Okay. That's it. Okay. All right, and then these guys are friends. They're holding hands now. So what was happening with this? Does anybody want to tell me what was happening with that? Yeah, what do you think?
They were all like evenly charged, so they didn't want to be next to each other.
Right. So there are electrons accumulating in this right here, and then these strands are insulators, and so these end up getting polarized the same way that these do, and that causes them to repel outwards. Okay. All right. Let's see, where are we going next? Okay. Okay, so this is going to get into Coulomb's law and doing calculations again. So something I wanted to talk about here, and I did post on Course Networking this morning about this. There are two ways that you can do calculations with Coulomb's law. I'm going to go through both ways so that you can see them, because a lot of people were commenting about R hat, right? People saw the R hat in the videos. Who saw that? Yeah, it might have been a little confusing, right? So I'm going to try to talk about these two methods of doing calculations with Coulomb's law, what the difference is between them, and how you can use either one. Ultimately, you can use either one because they are equivalent. So as I said, there are two methods to solving problems with Coulomb's law. The first method is what I would call the magnitude of force and opposites attract and likes repel method. So what this method does is it takes the magnitude of the force, and then when you have the magnitude of the force afterwards, you can figure out what the direction of it's going to be based on whether the charges are going to attract each other or repel each other. This is the method the book uses. I say it's easier in quotations because you don't have to use unit vectors. It's not actually calculationally easier per se because it requires you to do one additional step, and that is at the end you need to fix the direction of the force by saying that these are like charges or opposite charges. Now the other method is the unit vector method. This one requires you to be able to use unit vectors. It's the harder method in a sense because you have to understand unit vectors very well in order to use it, but it does require one less step when you do the calculations. So both methods will give you the right answer, and so in physics, if you have two methods and they give you different answers, then one of the methods is wrong. They always have to give you the same answer. You're going to, if you can understand both methods and why they're the same, you'll be very well prepared for any questions that we ask you. And I'm going to demo both methods here, but ultimately I'm going to be using method 2 when I do my solutions. Okay, so to outline this, to start out with, I'm going to show method 1 first, and then show you method 2. So method 1 really relies on saying that you're going to take the absolute value of the force is going to be equal to K times Q1, Q2 divided by R squared, and take the magnitude of both of these charges. So what we're doing is we're getting rid of any negative signs in this. This is always going to be positive. Okay, so let's look at an example of how we can use this. See if I can get a better piece of chalk too. This one looks good. Let's see an example of how we can use this. Okay, so if I have a charge Q1 at the origin and a charge Q2 that I'm going to say is at a position AB, so along the x-axis this is a distance A, and along the y-axis this is a distance B. I want to find the force vector, F vector, that points from 1 to 2. Or I want to find what the electric force is acting on charge 2. So if we were going to do this with the magnitude and direction of charges method, the way that we would do this is we would set up the equation exactly the way I have this written here. So I would say the magnitude of F12 is going to be equal to K magnitude Q1 magnitude Q2 divided by R squared. Now we need to ask ourselves what R squared is. By definition, R squared is the distance from charge 1 to charge 2. So based on this diagram I have here, this is the distance R. Okay? What is R for this particular problem? How can we find R? Pythagorean Theorem, right? So what is R here? Good. So R squared is equal to A squared plus B squared. And so what this tells us is the magnitude of this force, F12, is equal to K times the magnitude of Q1 times the magnitude of Q2 divided by A squared plus B squared. Okay? So the next thing that we need to do, because we want to find the force vector, we need to know what the components of this force are, right? Because we just calculated what the hypotenuse of this triangle is, right? Effectively, right? So if I draw this triangle again, this is F12 as a magnitude. But what I need, put an angle theta here too. What I need is Fx, or the magnitude of Fx, and the magnitude of Fy, right? That's going to give me a vector. Vectors have x components and y components, and so from the hypotenuse of this triangle, I can find what Fx and Fy are, because if this is the angle theta, how is this going to relate to this angle theta in F12, the magnitude? The trigonometric identity, cosine, right? So this is the adjacent portion here. So this is going to be the magnitude of F12 times cosine of theta. And that leaves this one being what? Sine, right? So this is F12 times sine of theta. So now if I want to calculate this, I can say the magnitude of Fx is going to be equal to, I'm not going to write this down again, because I have it here, but this is going to be F12 times the cosine of this angle. What is the cosine of this angle from our diagram? in general, cosine is adjacent or opposite? Adjacent, right? So this is, what's the adjacent part of the triangle for the dimensions that I have here? It's A, right? Right? So this is going to be A divided by R, which is A squared plus B squared, now to the 1/2, right? Because cosine of theta is A over R, okay? Now if I want Fy as a magnitude, this is the magnitude of F12 times what? What's the sine? Sine of theta is what? B over R, and so this is going to be B divided by A squared plus B squared to the 1/2. Okay, so we calculated what the magnitude of the force is that Q1 acts on Q2, and now we've also calculated what the X and Y components are. Now the last step in this method, if you want to do this with the magnitude and opposites attract and likes repel method, is to write the final force vector F12 is going to be equal to the magnitude of Fx times x hat plus the magnitude of Fy times y hat. Okay. Now, there's one other thing that I need to incorporate here, and that's whether these two charges attract each other or they repel each other. Right now, I've just given you some arbitrary charges, an arbitrary Q1 and an arbitrary Q2, but I haven't told you which of them is positive or which of them is negative. If they're both positive, they're both negative. If one of them's positive, one of them's negative. So if we say that this Q1 is positive and this Q2 is positive, what's the direction that this force is going to point? They're going to repel each other, right? Which means that this force is going to go this way, right? Does everybody see that? If these are the same type of charge, they're both positive charges, they repel, right? In which case, the equation that I have written here is already correct, right? Because this is a positive X portion is going to point this way. This is a positive Y portion points this way. So if these are the same type of charge, this equation's correct already. Now, what's going to change if I say that this is a positive charge and this is a negative charge? What do you guys think? Right here. What's going to change if it's a positive charge and a negative charge? The direction. The direction's going to change. How is the direction going to change? Say again? Negative. Yeah, it's negative. Both of these are negative then, right? So I'm going to say that this is plus or minus. So in determining this plus or minus, you need to ask yourself, are these charges the same or are they different? And if they're different, these things are going to attract each other. If they're the same, they're going to repel each other. And the answer that you get in this last equation needs to reflect that. Okay? So this is the first method. Any questions? Now, I'm going to show you the second method, and you might see why I prefer the second method after I show it to you, because you have to do a lot of funny things with absolute values when you use the first method. Okay. Now, the second method is actually what I did in my video, and it's also indirectly what was done in the video that Dr. Marius posted. The second method says, well, if I want to find what the vector is that goes from 1 to 2, why don't I just start by writing an equation that is a vector equation. So this is F12 vector is equal to K Q1 Q2 divided by R squared times R hat. And now you'll see a difference between this equation and the first equation that I wrote in two ways. The first way is now I don't have absolute values on these charges. So when I plug in the charges that I have here, if I have a negative charge, I plug in a negative charge here. If I have a positive charge, I plug in a positive charge here. This unit vector is also new. And this unit vector is going to be the unit vector that points from charge 1 to charge 2. So this is the unit vector r hat. So you see it's pointing this way. Q1's down here, Q2's up here, and the unit vector that points that way goes like this. Okay, so now, in order to do this one, I need to establish what the unit vector R12 is. And so in order to do that, I can draw another small triangle here, and put an angle theta here. So this is r hat. What's this side of this is r hat? Remember, r hat has a magnitude of 1. Is this a sine? Is it cosine? Tangent? Cotangent? Cosecant? Cotangent? Cosine, right? This is cosine. This one? Sine. And so this is the y portion and this is the x portion, which means that the unit vector r hat is going to have some portion cosine of theta times x hat, plus some portion sine of theta times y hat. Okay? Now, we remember this part doesn't change. R is still just going to be, or R squared is going to be A squared plus B squared, right? So I can plug that in here. And I can also remember that cosine of theta was A divided by A squared plus B squared to the 1/2 times x hat, plus b divided by a squared plus b squared to the 1/2. Am I starting to write a little small for the people in the back? Can you still see this?
These things?
What was that a yes? I'm writing small? Yeah. Okay, let me write this again. So this is a divided by a squared plus b squared to the 1/2 times x hat, plus b divided by a squared plus b squared to the 1/2 times y hat. Okay, so we're already seeing we're getting back a lot of the same terms that we had for the first method, as we should. So now let's finish this and put these together. So I have my r squared that's going to go here. I'm going to have my unit vector that goes here. And so in the end, what I'm going to have is f vector 1, 2 is going to be equal to k q1 q2 over a squared plus b squared times a divided by a squared plus b squared to the 1/2 times x hat plus b divided by a squared plus b squared to the 1/2 times y hat. Okay. Now when we're looking at this one, what's going to be different about this one? I don't have any absolute values in this anymore. So I don't need to do an extra step to decide what direction the force is going to act. Because I did it this way, the force is naturally going to point the way that it should. And let's see why that is. Was there a question? No. Let's see why that is. If I have two positive charges, is this equation going to be positive or negative? Positive, right? Because I have a positive times a positive. That gives me a positive. If I have two negatives, say this is an electron and an electron, is this equation going to be positive or negative? It's going to be positive. If I have an electron and a proton, is this equation going to be positive or negative? It's going to be negative, because when I plug in the charge here for an electron, this is a negative charge times a positive charge, which makes the entire equation negative, which means that it's going to attract to the origin. Okay? Any questions? This is a little tough, and it might take a while to sink in. But like I said, there are these two ways to do these problems. So if this seems daunting to work with unit vectors, then by all means use the first method that I outlined. Okay? So I'm going to actually break this portion that I just did for these forces. I'm going to take that portion out. It's going to be in the main video, but I'm going to make a separate video that's only that. So if this is something that you need to watch a couple of times to understand, you'll be able to do that more easily. Okay. So now, let's actually do a couple of calculations, if I can find my slide changer. Okay, let's go back to one of the things that I asked you last time. Now, if you remember what the letter choice was for this last time, I'm sad to say that I changed it, so don't just say it's the same letter as it was last time, but make sure that you can calculate this. You can find what F or what K should be, because we know what the units of everything else are. So I'll leave this here. I'm also going to write numerically what K is. So K is going to be equal to 8.99 times 10 to the 9, and we'll put the units in afterwards. So let's talk about this one. Who thinks they know the right answer? Yeah? Who wants to tell me? You want to tell me? Yeah? It's B. Okay. That happens to be the correct answer. So let's talk about why it is the correct answer. So we know the units of force should be a kilogram times a meter per second squared. And we also know that the left side of the equation needs to match the right side of the equation. We have K here. On the right side of the equation, we also have a Coulomb squared per meter squared. And when we rearrange this equation to solve for K, that's going to leave us with a Newton times a meter squared divided by Coulomb squared. Or kilogram meter cubed per second squared Coulomb squared. Okay? All right, so now let's get into some real calculations. But before we do that, I want you guys to remember and define the superposition principle. So talk to each other, remind ourselves what the superposition principle means. So let's talk about this one. So the superposition principle says, or the superposition principle for electrostatics, superposition is actually something that comes up a lot if you take some more advanced mathematics classes. You know, some people might talk about linear superposition of solutions or something in differential equations, but here we're talking about electrostatic superposition. And what this means is if I have a collection of charges, and I want to find what the force is on this one. So say this is some charge 1, some charge 2, some charge 3, some charge 4. I want to find the force on charge 2. In order to do that, what I'm going to do is I'm going to find what the force is from 1 acting on 2, find what the force is from 3 acting to 2, and then find what the force is from 4 acting to 2, and then add all of those together. So you superimpose all of those individual forces to create an equation that incorporates all of them. So really what this says is that the fact that you have other charges here doesn't affect what the force is that this one acts on this one. This one still acts exactly the same force. So you're allowed to just add them together. Okay? All right, so now let's do some real calculations. So go ahead and spend some time working with your neighbor on this one. There's a question I might need to clarify here. So NC stands for what? Does anybody know offhand? Nano. Nano. What is nano? It's a thousandth of a micro, which is a thousandth of a milli, which is a thousandth of a meter. So that's 3 thousandths. Negative 9. Yes. So nano is times 10 to the negative 9. Let's go ahead and talk about this one. So we know that we have this charge Q2 that's in between some Q1 and some Q3. So this is Q1, this is Q2, and this is Q3. And they're separated by some distance of 2 centimeters. Now Q1 is going to be a positive charge, and this is going to be equal to plus 2 nanocoulombs. Q2 is, I believe, a negative charge, so this is minus 1 nanocoulomb. And Q3 is going to be also a negative charge. This is minus 3 nanocoulombs, okay? So we want to find what the force is on Q2. So let's first start by writing down Coulomb's law. So like I said, I'm going to be doing this in method 2, but you can equivalently do this with method 1. So the force that charge Q1 acts on Q2 is going to be equal to K Q1 Q2 times the unit vector that points from R1 to R2 divided by the distance between R1 and R2. So we know that this distance here is going to be 2 centimeters. We need to convert this to meters because our constant K is written in terms of meters. And our charges also need to be written in terms of coulombs instead of nanocoulombs. We also know that the unit vector that points from Q1 to Q2, if I'm doing method 2, that's what this means. It always means the unit vector that points from Q1 to Q2, irrespective of whether it's a positive or negative charge. It's always from 1 to 2. So to go from 1 to 2, this is the positive x direction, so I say this is a positive x hat. So I say R hat 1, 2 is going to be a positive x hat. Okay. Now let's plug everything in. So this is going to be equal to 8.99 times 10 to the 9 Newton times meter squared per Coulomb squared times 2 times 10 to the negative 9 coulombs times negative 1 times 10 to the negative 9 coulombs times a unit vector in the positive x hat direction. Okay? Now this is going to be divided by the distance squared. So the distance is 2 centimeters. To make this meters, we divide by 100. 2 meters squared. And when I do this calculation, this is going to give me negative 4.4 times 10 to the negative 5 newtons in the x hat direction. Okay. Now just to pause here and refer to what you would have if instead you use method 1. If you had used method 1, this wouldn't have a unit vector. This and this would both be positive. You would get a positive answer here, and then you'd have to ask yourself, well, what's the direction of the force that Q1 acts on Q2? That's going to be in the negative x direction, and so you recover the same answer if you decided to do it like that. Okay, so let's find what the force is that charge 3 acts on charge 2. So this is going to look very similar. The Q3 is going to be a little bit different. So we're going to have K Q1 Q3 over R squared times R hat from 3 to 2. So we need to address what this R hat 3, 2 is. As I said, always by definition, this unit vector points from the first charge to the charge that we're finding the force on. And so from Q3 to Q2 is the negative x hat direction. So negative x hat direction. And so now when we plug everything in here, this is going to be 8.99 Newton meters squared per, the new chalk, meters squared per Coulomb squared times negative 1 times 10 to the negative 9 coulombs times negative 3 times 10 to the negative 9 coulombs times negative x hat divided by, again, r is the same distance that it was before. This is 0.02 meters squared. And this is going to give me an answer of negative 6.7 times 10 to the negative 5 newtons in the x-hat direction. And again, I can see that my directions worked out naturally when I use method 2. We know that, and you can always, even if you use method 2, you should always check to see if it did indeed work out the way that it should, by looking at this and saying, well, what's the direction this should go? This goes from, these are two negative charges, they repel each other, that's going to make it go this way, which is the negative x direction. And that does indeed give us the direction that we expect it should. So now, to complete the problem, all we need to do is just add these,
If we were doing something like this on a test, would you make us use one method or the other?
No. It's whatever you were more comfortable with. Now, the only caveat to that is, depending on who writes that particular question, it might lend itself a little bit more to one method or the other. But as long as you use either method, you're clearly showing all of your steps, then you'll get the right answer. You get full credit. Yeah. Okay. All right. So now, the next thing that we want to do is, and that's just the last thing, is to find the total force on Q2. We impose the superposition principle and just add these two together. So F total is going to be equal to F12 plus F32. And this is going to be equal to, drum roll please, negative 11.1 times 10 to the negative 5 newtons in the x-hat direction. And we have, again, with this equation, when I just added them together, it gives us the right answer because I was consistent with all of my unit vectors. Okay? Any questions about this one? No? Okay, let's move on to the next one. So now we're going to kind of turn this around a little bit and do this from the side. So now we're doing this in 2 dimensions. Oh, you can always tell it's a good day when your pants are covered in chalk. Okay. Okay, so let's go ahead and talk about this one. So somebody just asked me a question that was, it was a good question because it's something that I don't know if I clarified well enough. And that is, what is this x hat and what is this y hat? Like if I have an equation, I need to plug something into it. What do I plug in for x hat and what do I plug in for y hat? And the answer is that there's nothing to plug in for x hat and y hat because x hat and y hat are just labels to tell you that whatever is multiplied by x hat is in the x direction. And whatever is multiplied by y hat is in the y direction. So whenever we have a vector equation that has an x hat and a y hat in it, in any discipline, any physics problem we solve, it, whether it's in electrostatics or if we go back and do momentum, anytime we have this x hat, that means everything multiplied by that is happening in x. And everything that's multiplied by y hat is happening in y. Okay. Does that clear things up a little bit for some people? Yeah. Thanks for that question because sometimes I do gloss over these things. Okay. So let's go ahead and solve this one. So I have my drawing here, but let me talk about why I have things labeled the way that they are. I'll erase it and start over a little bit. Okay. So this is 2 centimeters. Jeez, I don't know what it is about this room, but it is hot. Okay. So, okay, yeah, this is the right problem. All right. So what I did here was in this problem, every time that I've been using Coulomb's law so far, I've been talking about what charge 1 does to charge 2, or charge 2 does to charge 3. Well, that's not labeled here. I don't give you any 1s and 2s here. So something that I like to do, and I'm sure a lot of the more experienced physics people probably do the same thing. When somebody doesn't give you a label, empower yourself to make up your own own label, right? Because you want to keep track of things here. So I'm calling this one at the origin 1. I'm calling this one at the right 2. And I'm calling this one up here 3. Okay? So to find what the force is on 2, let's first start by finding what the force that 1 acts on 2, and then we'll find what the force that 3 acts on 2. So the force that 1 acts on 2 is going to be equal to K Q1 Q2 over R squared times our unit vector that points from R1 to R2. Okay? So now I just need to plug in what I have here. I need to evaluate what R is, and I need to find what the unit vector is. What is the unit vector that points from 1 to 2? X, right? It's just X hat. It points this way along the x-axis, and so R12 is equal to positive X hat. Do we all see that? If I'm throwing something from here to here, I'm throwing it in the positive X direction. So that's going to be positive X hat. What is R? It's 2 centimeters, right? We need this to be in SI. So this needs to be 0.02 meters. And we have our charges here. So we can plug everything in. And so all of these charges have a magnitude of 6 microcoulombs. This one's going to be positive in the bottom left, and this one's going to be negative. So this is going to be 8.99 times 10 to the 9 newtons times meters squared per coulomb squared. I'm just going to erase this and move it up so I have some room. So this is R is equal to 0.02 meters. Times the positive charge, which is 6 microcoulombs, so 6 times 10 to negative 6 coulombs, times the negative charge, which is minus 6 times 10 to the negative 6 coulombs, times our positive unit vector. This times it might be easier to be left-handed. Times our positive X hat unit vector divided by 0.02 meters squared. Okay? So now I just need to plug all this into our calculator and turn the crank, and what I end up finding is this is negative 809.1 times X hat, newtons. Newtons times X hat. Okay? Units matter. Pretty much every problem that we have on a test, there's a point for writing the units, so make sure you write your units. Okay. Now, if I wanted to do this the other way, if I wanted to use method 1, what I would see is I would have absolute values here. I have an absolute value. Everything here would be positive. And then I would just have to ask myself what the direction, the force that this acts is. These are attracted to each other, and so this is going to pull it this way. Okay? Now let's look at the tougher part. This is calculating the force that 3 acts on 2. So this is the force that 3 acts on 2. And again, the starting equation almost always looks the same. So this is going to be K Q3 Q2 divided by R squared times R hat 3, 2. All right, so let's start first by finding what R squared is. If we remember, this was what this looked like. This was this is 2 centimeters. This was 2 centimeters. How am I going to find where R squared is? Come on, you guys know this. All together. Pythagorean Theorem, right? So R is going to be equal to the square root of a squared plus b squared, and so this is going to be 0.02 squared plus 0.02 squared, which is going to be equal to 0.0008. So I'll just carry that around later and find a new piece of chalk. Okay. The next thing I need to do is find what R hat 32 is. So to find r hat 32, we know that this is going to be pointing down like this, right? The unit vector that points from here to here is going to point down like this, right? If I'm going to throw my ball from here to here, that's the way that it's going to go. This makes some angle theta here. This is the same angle theta here, right? Yeah.
You have to take the square root of 0.0008.
You just did r squared, not r.
Oh, sorry. Yeah, this is r squared.
Between 0.02.
R squared is that better?
No,
It's 0.0.
What is it?
the square root of
He's just telling you that r squared is 0.008.
Right. So r squared is, yeah, okay. Numbers, who likes them, right? Is that better? Yeah, I need an r squared here. I'm just going to plug that in later. Yeah. Okay. All right, so let's come back to our unit vector. We know that this is going to have some part in x hat and some part in y hat, right? So now we just need to figure out how much in x hat and how much in y hat, right? How much in x hat is going to be how much of this is along the x-axis, and how much in y hat is going to be how much this is along the y-axis. So this is the adjacent side to this angle. This makes this a cosine of theta, and it's in the positive x direction, so this stays positive here. Now, this part is the opposite of this angle, so that makes this a sine. And additionally, this is pointing down, which makes this a minus sine of theta. Okay? So the other thing that I need to do is I don't know what theta is, so I need to write this sine and cosine in terms of theta, or in terms of the sides that I have here. And I know actually that since this is 2 centimeters and this is 2 centimeters, what should this angle be? It's 45 degrees. What's cosine of 45? Anyone know offhand? 1 over root 2 or root 2 over 2, right? So this is root 2 over 2, x hat minus root 2 over 2, y hat, okay? All right, now I have my r hat 32, I have my r, I just need to put everything else together in order to finish this calculation. And so f vector 32 is going to be equal to 8.99 times 10 to the 9 newtons Coulomb squared, newtons meters squared per Coulomb squared, times negative 6 times 10 to the negative 6 coulombs, times negative 6 times 10 to the negative 6 coulombs, divided by 0.0008 times this r hat. Now I don't have room to write this in here, but this is what r hat 32 is, and that goes right here. So then after I plug that in, what I end up finding is that f32 is going to be equal to 286 newtons in x hat minus 286 newtons in y hat. And now to find what the force is, the total force, F total, this is going to be equal to F12 plus F32, okay? And that's it. Now, then if I wanted to do the second part and I wanted to find what the magnitude of F total is, everything here would have X and Y components, and then I could use the Pythagorean Theorem just to find what that magnitude is, okay? Any questions about this? Okay, so that's going to be it. We'll pick up again with Coulomb's law and start electric fields on Tuesday.